get up from it and you're like,
Yeah,
Yeah.
right.
Two different ways to memorize things. Yes.
Like highway quick tricks, and then the other one
it was number
Standing
7,
by
but
that
I think I did wrong.
Exactly.
Yeah.
No, I think you just had the wrong height and radius, but everything else was like set up correctly.
Oh, cool. Wait, did you grade mine already?
Yeah.
Pretty good.
Oh,
Yeah, it's already
I
posted.
want that like off my to-do list.
okay. It's just not in for me.
Yeah.
Oh, really?
Are you sure? I entered it in
Go
earlier.
to below.
Hey everyone, how are y'all? Couple of things to mention. The exam key for exam 1 is up. All the exam keys will go here after the exam. I recommend that you look through what you missed and then compare that to the key, just so you can try to learn from what you missed. And then ask me any questions if something doesn't make sense, of course. And then blank exams I'm posting here. So usually towards the final, people like to print those off and just kind of like take them, just to see what they remember. So the blank exams will be posted as well. I'll hand back your exams at the end of class. I'll try to remember to stop around 8-ish to give those back to y'all. For now, we're going to start chapter 8. And in chapter 8, each section is a different type of integration technique, except for the very last section of chapter 8. We're going to look here at just like basic approaches, and then in 8.2 we'll start to get definitive techniques to integrate. Okay, so the basic integration formulas here, you should know these. If you know these, it can expedite integration quite well. Really these two here, 11 and 12, they're really common integrals, antiderivatives. So you should definitely know those as well. Inverse secant is not as common as inverse sine and inverse tangent, but as we'll see when we get into like chapter 8.4, if you don't remember these, you can't. There are integration techniques that will give you inverse sine or give you inverse tangent, but again, it's much more conducive and much more efficient to just know those right now. Because if you don't recognize inverse sine and inverse tangent, you're going to try like use substitutions and rearranging things, and it's not going to work out. So for sure know those two as well. And the use substitution was something that undid the chain rule. So like if we take the derivative of a function using the chain rule, that's the use substitution is undoing the chain rule. So you can think of use substitution as a reverse chain rule. I'm just going to write this here. I don't know that we need to find these derivatives and stuff, but we've got the derivative of the outer function. The inner function stays the same, and then we multiply all of that by the derivative of the inner function. So that's the chain rule applied to a derivative, but the use substitution comes in when we're taking the antiderivative of something like that. So that's where use substitution is most straightforwardly applied anyways. Most of the integration methods in this, well, I shouldn't say that, but a lot of the integration techniques here in 8.1, they simply deal with multiplying your function by a form of 1. There's some factoring that we look at, there's long division we look at, but those are like the most common sort of algebraic procedures that we see here in 8.1. So derivative of sine of 5x rather, cosine of 5x times the derivative of 5x there. So again, that's chain rule. If we had to find the antiderivative, hopefully you already know what that is just from the table up here. But again, if you didn't, use substitution undoes the chain rule. So hopefully nothing new there. We can do this here as well, but I don't know that's pretty well. So I'm not sure why I put this first. Example 1, I want you to, if you have the packet, let's go to, before we address that, let's go to example 4. I should have put that example after this one. But whenever you have an integrand whose degree, like if you've got a rational function, if you've got the degree of the numerator being larger than or equal to the degree of the denominator, that's what they call improper. And so to simplify those or to look at them differently, we use long division on those things. Okay. So that is addressed there, but we're going to go back to example 1 because it's sort of needed. Not immediately, but this is one where it says multiply. Most of them won't say, they'll just say integrate, right? But we're going to just, in our instructions, kind of give indications of what we're supposed to do. And really it comes down to like a pattern recognition, like the more of these you do, the more patterns you recognize and say, oh yeah, when I have this particular situation, I should do, X, Y, and Z first. So it does say multiply by a form of 1 to create a function that is possible to integrate. So, these weird negative exponents in the denominator, we're going to multiply through by x cubed over x cubed, just so we can get rid of the negative exponents.
You can't just bring them up.
Do what?
Never mind. I was going to say, you can't just bring them up, but you can't because they're added, right?
Right, because they're added. If it was like x to the -1 plus x to the -3, it would have to be like, that all of that would have to be to a negative power as well before you wrote it like this. Well, you would still have those negative powers. You can't do that individually because it's added together. Okay, so what we get is x cubed over x squared plus 1. All right, so it's important to recognize situations where you do have an improper fraction. The degree of the numerator is larger than the degree of the denominator. So we'll say this is, improper. We have to use long division. So we'll do that over here, I guess. Okay, so we're going to divide x cubed by x squared plus 1. It might have been a minute since you've done this, but what we're looking at is the leading term here on the divisor, and we're asking, what do I need to multiply that by in order to get x cubed? So if I multiply the x squared by x, I'm going to get that x cubed right there. And it's just like division with numbers. Now we multiply these two things together, so we have x times x squared, x times 1. With numbers, what do we do with this? When we divide numbers, long division with numbers, you have to subtract. So you have to subtract all of this. Okay, so we have 0 and we have a negative x. And we're done, right? X, there's nothing we can multiply as far as like integer powered or natural number powers to get x from negative x. So that's, in this instance, this is our remainder, and the x up top is the quotient. So now we've got to remember, once we have this information, how do we rewrite x cubed over x squared plus 1 based off of this? Take the quotient plus the remainder over the divisor. So we'll write that out just because we see a few of these. just write it. The divisor, the thing you divide by. So that's kind of the format you get after long division. That's how you rewrite your expression. Okay. So typically that will help. I mean, there's no guarantee that it will, right? That's the thing with antiderivatives. We can easily check, is our antiderivative correct by just taking the derivative, but the process of finding antiderivatives is much harder than finding derivatives, for sure. So we have this now turning into the integral, or the antiderivative of x minus x over x squared plus 1. I know it's a nitpicky thing, but if you've got multiple things in front of the integrand, put those in parentheses before you write your dx, because that dx is actually applied to all of those terms. You know, I know technically you should do that, but like, you know, I'm not gonna, if you're writing things like this, I'm not taking points off for it. You just shouldn't write it this way. I mean, you know what that means when you write it down, but it's just technically not correct to write it out like that. Okay, so definitely helped us with this first term, right? Find the antiderivative of x. What about the antiderivative of x over x squared plus 1? Can we do that? Yeah. So this right here should be a u substitution, or did we talk about logarithmic form? I think we talked about that in chapter 6, didn't we? Yes. Log form. So the way we think of the logarithmic form, maybe we can add another page, but remember the derivative of the natural log of a function is the 1 over the function times the derivative of the function. Remember that? Derivative. Therefore, if I looked at the antiderivative of this thing, the antiderivative of this should be equal to this, plus c. So, you know, if you can recognize that pattern, it saves you time because you don't have to do a u substitution. If you don't, if that's weird to think about it that way, then just do a u substitution. Either way, you're going to get there. The problem is this is not quite 100% f prime over f, right? The derivative of this thing here is going to be 2x. So we could say, well, you know, it would be directly f prime over f if we had a 2 up here, right? I mean, we can't just add the 2 up there without, multiply the 2 up there rather, without doing something else in return. Okay. So that's, you know, I guess we can look at it that way or through a u substitution. But before we do, we're just going to break this up. We have the antiderivative of x dx minus the antiderivative of x over x squared plus 1 dx. Okay, so I'm just going to write that here. If we had a 2x there, then it's in logarithmic form. But like we said, if we're going to multiply the expression by 2, then we also need to divide it by 2. Does everybody agree with that? Okay, so that's in logarithmic form. If, like I said, if that doesn't make sense, then you're gonna, from here, you're gonna let u equal to x squared plus 1 and go through that whole spiel. Okay. So we have our x squared over 2 minus our 1/2 minus our 1/2. Now that thing is in logarithmic form, so it's just the natural log. You know, you should get in the habit of putting the absolute value because that is technically what it is. Plus, you know, we'll just call this c. We have 2 constants of integration if we split it up, right? So one constant here, another constant here. We add those together, we get a constant. Okay. So that's our antiderivative there. The only thing that we could try to modify is the absolute value here. In this instance, it's not necessary, but that's about the only other simplification we could do. So it's quite involved, right? We had to multiply by a form of 1. We had to do long division, and then potentially another U substitution. Okay, so I'm just going to put the parentheses here since x plus 1 is always positive. Anyone have any questions? So the main idea really of 8.1 is just to see some variations on strategies. When you start doing your homework, it's not going to say, hey, do this and then do that. It's going to be up to you to sort of trial and error through that antiderivative. So we're just sort of piecing together the tools that you're going to use. It's not, like I wouldn't recommend, like if you look at this problem, most people are going to be like, oh, I really don't know what to do. Here the computer's going to solve it for me, or going to give me a hint. I really advise against that. Like for me, a lot of the times when I look at antiderivatives, it's not immediate what I should do. Still, because they're hard. So you just look at it and start trying stuff. Okay, with trig functions, we'll see trig functions again in like 8.3, I think. And there's a couple of procedures we look at in 8.3, but oftentimes we can just rewrite them using various identities, keeping in mind that we want something here that we know what the antiderivative is, or that we could use U substitution to solve. So any ideas on this? What we have sine cubed over cosine to the 5th. Try to think of trig functions that we know how to integrate, and that might help guide your decision.
So we split like cosh, like we have 10 over the time like the sec square.
Right. Yeah. So so you're thinking of like tangent and secant squared. Like I can integrate secant squared is really the most important thing here. So I'm going to write this as sine cubed over cosine cubed times 1 over cosine squared. Yeah. But again, I'm not guaranteed that that's going to help, right? Like this was a suggestion, and if you want to go immediately into this step, that's totally fine as well. This is the suggestion. Write it as tangent cubed times secant squared. So there's nothing wrong with what we've done, and the question is does that help us? Does that allow us to compute the antiderivative?
We can use some substitutes with tens.
Mm-hmm.
We call U by equal to tens, and that one we use like the equal like secant.
Yeah, exactly. So the derivative of tangent is secant squared. So we're looking at a U substitution. This function, its derivative is right here. So that's a U substitution. We're going to say U is going to be tangent. That way du takes care of the rest. Derivative of tangent secant squared. So all of that's du. So it just turns into u cubed du. Again, maybe that's not totally obvious, but that's why it's important to recognize functions versus their derivatives, because you can say, well, you look at that and you immediately see that it's a u substitution because the derivative of tangent's sitting right there. Okay, and that's, pretty much it. You got the antiderivative of u cubed. Is that. And then we just resubstitute for tangent. Tangent to the 4th over 4 plus c. I'm not really, like on the exam, if you forgot c, I didn't take off points. For the most part, for us, it's not terribly crucial, but you'll see that when we get into the sections for differential equations, and when you start looking at differential equations, those constants absolutely matter. So it's a good habit to get into to track these constants. Okay, any questions on that? So as always, the trick with trig functions are the limitless identities that apply to them, right? Usually these things the identities are pretty straightforward. They're not these weird one-off identities that you saw one time. They usually stick to the main ones, the Pythagorean, the double angle, that kind of thing. Okay. And oftentimes more than one approach works, but this one does say split up the fraction to create. So that's always a viable option. If you've got a bunch of stuff added or subtracted, divided by a single thing, generally you want to split that up. So that pattern should be sort of well recognized at this point. We've got some things added, divided by a single thing. So when we split these two up, you're basically splitting it up into more manageable pieces when you can. So like this plus this over this. And then you just want to simplify what you have. So we're going to simplify this. That's 4 times e to the negative 3x plus e to the negative 5x. Does that make sense? So like I said, when you see things like a fraction and there's a bunch of things added or subtracted, divided by a single term, that's typically, you could try that approach where you just split everything up. So what's the antiderivative of 4e to the negative 3x?
Negative 4/3 e to the negative 3x?
Yes. Negative 4/3 e to the negative 3x. That's, I think, I don't know what number it is. Number 9? With a being negative 3. And plus the antiderivative of e to the negative 5x, same thing, it's e to the negative 5x divided by negative 5. So definitely, if you're not familiar with the ones on the first page, like study those, look over those. Save you a whole lot of time. Otherwise, that's a u substitution. U is negative 3x here, u is negative 5x over there. It's kind of tedious. So the other thing that we could try here is multiplying the top and the bottom by 1 in the form of e to the 2x over e to the 2x. Get rid of that negative exponent. But you would still have to split up the fraction if you did that. So you could try that if you wanted. Any questions on that? So this one again is improper. Like I said, usually on the exam or on the homework, it's not going to tell you that it's a certain thing. You just have to recognize it. So improper fraction, we're going to then divide x squared plus 4 by x plus 6. So again, really, we're looking at this leading term here. What do we multiply to get x squared? Multiply x by x. Multiply, or distribute rather. We've got x squared plus 6x. Then we have to subtract that whole thing off. So we have 0, we have 4 minus 6x, right? Or we have a minus 6x plus 4, 4 minus 6x. And then we start over. Leading term out here. Again, what do we need to get a negative 6x? Negative 6. Negative 6 times x. Negative 6 times positive 6. And then we subtract off that whole thing. Get 40. Is everyone okay with that? I'm not sure how long it's been since y'all seen long division. If that's weird, if you're unfamiliar, if you forgot, please email me. I'll find some resources. But it's just like long division with numbers. Like if we're dividing 337 by 2, it's the same process. Okay, so we're going to express now x squared plus 4 over x plus 6 as our quotient plus the remainder over the divisor. This is our divisor. Okay. So we're just going to rewrite over here. Oh, nice. That's weird. To just like get rid of everything. No, I don't even see the mouse anymore. It's something weird I'm not sure where our stuff went. Nothing seems to be functioning here. I might have to restart. I might have lost all that too. All right, sorry about that. No clue what caused that.
Well, it's constant. Let's see.
Okay, so we have our quotient plus our remainder over the divisor. I think that was right.
Yeah.
Okay. Okay, integrating x, antiderivative of x, antiderivative of -6, yeah. And what's the antiderivative of 40 over x plus 6?
40 natural log of x plus 6.
You're right.
Let's see.
That's another logarithm form right there, right? Derivative of x plus 6 is 1. So you already have that. The 40, you just think about it as a constant. So x squared over 2 minus 6x plus 40 times the natural log absolute value of x plus 6, all plus c. Other, I guess, we could also write it here if it's not making sense. So I guess, you would say u equals x plus 6, du is dx. I'll put this 40 out here, antiderivative of 1 over u du. So that's antiderivative is the natural log absolute value of u times 40. That's all right. That's our final result there. So honestly, if you have time, you can check your work, right? If this were an exam question and you're like, well, maybe I messed something up, just take the derivative of this, simplify it, you get x squared plus 4 over x plus 6. With the derivatives, it was nice because you had formulas to say this is how you take the derivative of this, but you had no way to check. You just kind of hoped that you took the derivative correctly. Here, at least, the process is difficult, but you can check your work. I don't know. There's always a compensation, right? There's always a trade-off. Okay, so any questions on this one? Yeah, comes back, comes back. So something like this where it's not an improper, right? The degree of the numerator is not larger than or equal to the degree of the denominator. We look at that and we say, well, will a u substitution work there? Could we do a u substitution? Your option is maybe to try this bottom part. If I let u equal to x squared plus 4x plus 8. I know it says complete the square, but we're just kind of running through our options at this point. It's not improper, we wouldn't divide it. Would a u substitution work? We see why it doesn't work. Right? If you can take your u substitution, if we could have taken this right here and somehow solved for that x up here, then yeah, it would have worked out. But, we could solve for x in our differentiated substitution. But then that throws in another differential in there, and we don't want that, right? Sorry, this is actually dx. But does everybody see why u substitution doesn't work? You can't really get too clever with that. It just doesn't work. So no u substitution, no improper long division. You really couldn't multiply that by a form of 1. That would change that polynomial at the bottom. So the only option, well, I guess maybe there are other options at this point, but what we're going to do is we're going to complete the square on this quadratic here. So we've got, think about the linear over the quadratic type situation. Probably want to complete the square on the quadratic. So what's the completed square version of this thing right here? Meaning, like, we want to write this thing as a completed square, like that, right?
X plus 2 whole square is 4.
So x plus 2
Whole square.
squared plus 4? Do y'all agree? So here's a quick reminder. Complete the square. You take half of the coefficient. You got to make sure that this is 1, which it is. You take half the coefficient of x. Sorry, let me scoot that over. You take half of the coefficient on x, so we're going to take half of 4. And then square that result. Half of 4 is 2, squared is 4. You add that with your x's. We have to subtract it over here. So we're adding in 0. So this thing right here factors as x plus 2 quantity squared, and there's our positive 4. So it's, quadratic ax squared plus bx plus c. We take half of the b term and square that, add to the x's. We'll just say x's like that. And then subtract from the constant. And caveat here is that that a has to be equal to 1. So this is if a is 1. If a is not 1, then you just got to factor a out. That's the only difference. Okay, so we've got our x over x plus 2 quantity squared plus 4. Now, this doesn't seem terribly helpful. We've completed the square, but it doesn't really look like it's any better, I guess. But what can we do with our new representation that we couldn't do with the old one? New substitution, right? So here, if we say we're going to now let u equal to x plus 2. Notice we don't have a u as a quadratic, so we can solve really straightforwardly what x is. Du is dx. Our substitution implies that this x on top is going to be u minus 2. So then we've got antiderivative up top is x, which is actually u minus 2. We have x plus 2 quantity squared, which was just our u, plus that 4. And the dx was the du. Everybody okay with that? All right, so that's where we're at. Where do we go? Was that helpful to even do?
Can you do the difference of squares?
Where?
Figured out the u plus 2 and u minus 2.
Oh, on the bottom, no, it's not a difference, it's a sum.
Oh, yeah, that's right.
Yeah. You could say it's, you could factor it in terms of imaginary numbers.
Yeah.
So okay, where we came from, x over x plus 2 quantity squared over 4, like there's nothing we can do with that. With the u minus 2 up top over something squared plus 4, we can split this up, right? So we could say that it's u over all of this stuff. Minus 2 over all that stuff. So that's something we can do, right? couldn't do that with the original one, x over square plus 4. So we can do that, then we look at both of these and say, are both of these something I can find the antiderivative of? What about u over u squared plus 4? Can we find the antiderivative?
Just substitute.
Yeah, substitution, or it's kind of in log form, right? Derivative of the bottom is 2u. We put our 2 out here, so we have it in log form. We have to multiply it by a half. So yeah, that's something we can do, u substitution or logarithmic form. How about 2 over u squared plus 4?
Reverse is about at 10.
Right, yeah. That one, that important one that we showed earlier. Number 12. So just think of 2 as a constant out front of the antiderivative. We've got our x squared plus 4 or u squared plus 4 on the bottom. So that is an inverse tangent antiderivative. So we can integrate, find the antiderivative of both of those now that we've split it up. So first one is simply 1/2 times the natural log absolute value of u squared plus 4. You know, if you need to, think of it this one here, like we're gonna just look at that as our du or our 1. We've got our 2 out here. We have minus 2. The antiderivative of u squared plus 1 over u squared plus 4 is what? Say that again, sorry.
Is it, so it's 1 over 2 arctan u over 2?
Correct.
Plus c?
Correct. So this is number whatever 12, right? Was it 12? With a equal to 2. So it's 1 over a inverse tangent of x over a. 1 over a inverse tangent of x over a. So if you don't recognize that, study it like you should. Immediately recognize that as arctangent, inverse tangent. The only other technique really that we see where we could handle something like that is trig substitution, and that's a really lengthy process. Substituting in trig functions to get the inverse tangent out, it's, there's a couple steps involved. So that's where we're sitting. We want everything though in terms of x, because that was the original variable. So we're just going to resubstitute for x. Have 1/2 ln was x plus 2 was u. That quantity is always positive, so we're just going to have, we drop the absolute value, minus inverse tangent of x plus 2 over 2. Yeah, I forgot our constants here, so my bad.
Is it better to keep it in the uncompleted, like the x squared plus 4x plus 8, or like that, or does it not matter?
X squared plus 4x plus 8.
So what it was before we completed the square?
Is it better to leave it like that?
To put it back into that, or is it?
Oh, yeah, I don't think there's a preference as far as expanding the x plus 2 squared out here. They're putting it back as the original quadratic at the bottom. If you want to do that, do that. That's really not that big of a deal, I don't think. But all right, there we go. And so, like simple functions, the antiderivatives, they're kind of complex. There's many functions. There's many functions that don't even have a known antiderivative. There's, I don't know, countless ones probably. But the classic example is e to the x squared. Like that function does not have a known antiderivative, meaning there's no technique of integration that we can apply to that to get something out of that. So they're called, depending on what text you look at, they're called non-integrable functions. So you can look at those things and see that there's many of them. So we don't know what function exists, so that when we take the derivative of that function, it gives us e to the x squared. But I think it's worth mentioning at this point, the kind of the next third of Calc 2 is we look at sequences and series. And sequences and series allow us to represent certain types of functions by infinite polynomials. So you know, if you had to integrate something like this, you say, well, the function doesn't have an antiderivative. That doesn't matter, because I can take a function like this and rewrite it as an infinite polynomial and just integrate the infinite polynomial term by term, evaluate from 0 to 2, and get an approximation of what that should be. So that's kind of like a good chunk of Calc 2. This kind of culminates to help us do things like that. So anyways, kind of just saying all this stuff so that when you do the homework and when you're practicing, that you are patient with yourself, because it is a difficult thing to do for sure. Any questions on that last example, I believe it was? Last example. Yeah, all right. And so those, hopefully, you know, kind of piecemeal some strategies to integrate. Save that. We should go lose it. The first technique that we get is integration by parts. And the integration by parts is going to allow us to undo the product rule. If we have a product rule, integration by parts, if you've got trying to do undo a u substitution, or sorry, a chain rule, that's a u substitution. So just to show you where the formula comes from, if we start off with the derivative of our product, first derivative of the second plus the second times the derivative of the first. Let me rewrite that. I'm just going to rewrite what we already have. So. All right, so if we know that's the derivative of a product, then we can sort of work this backwards to figure out how would I find the antiderivative of a product. So we're going to take the antiderivative of both sides with respect to x. Take the antiderivative of this with respect to x as well. So remember, if you know a derivative, you know an antiderivative. We're working this in reverse. The left-hand side, the derivative and antiderivative undo each other, so we just have that expression, or the integrand here, as u of x times v of x equals to, and then we're just going to split up the integral here. We have the integral of u prime times v dx plus the integral of v prime u dx. Everybody okay with that? Hopefully you follow. You don't need to remember this. I'm just trying to show you where the formula comes from. But hopefully you follow this. This this u prime is actually the different notation, derivative of u with respect to x. Same thing for the v prime. This v prime is actually the derivative of v with respect to x. So if we look at those two that way, then these differentials go away, right? This dx divides with this dx, and this dx divides by that dx. Does everybody see that? We should just write it out maybe? We'll write it out. Du over dx, v of x dx, plus dv over dx, u of x dx. Okay, these things divide out. So what we have is v du plus the integral of u times dv. So it's not that the dx, the integration with respect to x, isn't there anymore. It's just that it's masked because we simplified it. Okay, and all of this stuff here is still equivalent to u of x, v of x times v of x. And that's basically, I don't know if we have the integration by parts explicitly, but that's basically where the formula comes from. The last step is just to solve for the integral of u dv. Okay. So we're just going to rearrange our equation and say that the integral, instead of saying u dv, we'll just, or u of x rather dv, we'll say u dv. That's this integral here. We're solving for that. Is the integral, sorry, is uv, u of x, v of x, minus the integral of v of x du. So uv minus the integral of v du. And then we see here on the left-hand side, we could have easily solved for v du as well, the integral. But the left-hand side, we have a product. We have a function of x represented by u. And remember, dv is also a function of x. So you have these with a differential attached to it, right? This dv kind of absorbed that dx. So you have the product of two functions of x dx over here in disguise. And so if we start off with finding the antiderivative of a product, we're going to identify certain things that allows us to sort of break it apart, where a product uv doesn't involve an antiderivative, and we should have a simpler antiderivative to work with over here for the integral of v du. So that's integration by parts, the formula. Some people call that ultraviolet voodoo. So I think that's a pretty good mnemonic to remember. Just got to remember the integral and then the minus. Ultraviolet voodoo.
Also remember voodoo's a negative thing. Helps.
Oh, okay. Voodoo's a negative thing. I guess depending on what your proclivities are.
Yeah.
Think of voodoo happening to you.
I don't want to put anybody down if you're doing voodoo. That's hey, do your thing. Okay, so the process is to identify this right here, because this integral, this thing right here is given. This entire integral says find the antiderivative of all of that. That's going to be given to you. So we want to identify u and dv, and then we should be able to find v and du from those respectively. So if you identify u, you got to find this du by taking the derivative. When you identify the dv, we find the v by taking the antiderivative, right, the integral. So built into this antiderivative process are separate derivatives and separate antiderivatives. So there's, you know, a lot going on. You got to stay organized, otherwise you're going to be mixing stuff up. So this integral over here, the v du, it should be easier or the same difficulty as the original integral presented to you. And again, we know typical candidates for this are going to be products of functions, right? So like x times e to the x, x times sine x, those kinds of things are good candidates for integration by parts because they're products. Okay. So if you want to remember this, I just have this here so we can try to remember when you see a product of two functions, what you should let u equal. So another way to think about that is that whatever your choice for dv is, you should be able to find the antiderivative of dv because you need to find v. But the other way to think about this here is this acronym, whatever you want to call that, from left to right are hard to integrate to easy to integrate. So then we should let u be the leftmost letter that we see over here, right? Because if u is this function that's super hard to integrate, that's fine, because what we do with u is we take the derivative of it. We don't have to integrate it. So these letters are actually functions. These are logarithms. I is for inverse functions. And so yeah, with integration by parts, we can now find the antiderivative of our inverse trig functions. So like with the antiderivative of inverse sine, for instance, we could use integration by parts to find that. A are algebraic. That's things like x squared, square root of x, x to the 2/3, any polynomials, x to the 4th plus x squared minus 1, stuff like that. T is for trig, and E is for exponentials. So I don't know, maybe it's helpful for you to look at that. We're going to establish this as something we're going to use to identify what u should be. Because remember the process for finding using integration by parts, you have to identify a u and a dv. So this acronym, or whatever you want to call it, should help you identify what u should be. You should let u equal the leftmost function of that right there. So just for practice, we're not going to actually do these yet, but we will practice and see kind of what the process is up front to use integration by parts. So we have a product of two functions of x. Prior to this, we would say, well, there's a product of two functions of x. Well, actually, I don't know that we ever. I guess there were some instances. But that's the key that you should probably look at integration by parts. Two functions of x being multiplied. We have to identify u and a dv. So we're going to let u be the leftmost letter in that acronym. So that's our trig function, because we have a trig and an exponential. So pink and purple for trig. There's our trig function. That's our exponential function. So we should let u equal the trig function. Oops. So once we identified u, then we have what dv is supposed to be. So what's dv? E to the x. Is that it? E to the x. Remember when we sort of derived the formula that we had v prime of x? We wrote that as dv over dx. And when that multiplied the differential here from the integral, those two things canceled out and we just had dv, right? So your d's, dv, du, they should always contain differentials as well. dv is actually e to the x dx. I know it seems like a sort of a trivial thing, but it absolutely matters. So the d's should have d's. with them. Same thing here. Once we find u and dv, in order to find du, we have to take the derivative. You should put a differential here because we're taking a derivative. Du is the derivative of cosine dx, right? Because we're really taking the derivative of u with respect to x, and then we're just moving that differential over here so we have like variables with like variables. So derivatives, or I guess differentials with differentials. To find v, we have to look at the antiderivative of dv. Generally, we don't write that out, we just kind of figure it out. But that's what v is. V is the antiderivative. So our v is just e to the x. So you identify your u and your dv that's given to you in the original integral. Based off of that, we take the derivative of u to get du and the antiderivative of v to get dv. Excuse me, because we have to remember where all that's going. We have to then establish u times v minus the integral of v du to integrate by parts. Okay. Any questions on this?
Just keeps going in a circle.
That one does, yeah. But we can still solve that. We can still figure it out.
Eventually.
Yeah. So how about this one? What's our u?
X squared.
X squared. This is our, we'll just do this. X squared is our algebraic, sine is our trig. We have that acronym. I'm gonna let u be the leftmost function in that. U is x squared. We also need to identify dv. So dv would be,
sin x dx.
yes, good, sine x dx with dv. Okay, du is what?
2x dx.
2x dx. Good. And v?
Negative cosine.
Negative cosine x. Do you all agree? Antiderivative of sine is negative cosine. All right. That was our practice. We'll look at actual examples in a little bit. And yeah, you can do definite integrals with integration by parts as well. Okay, any questions on that? So maybe we'll look at a couple of these and just curious, who's done integration by parts before? Okay, so there is a shortcut for integration by parts that we can talk about too. But we'll take a break for now. The issue here is not, evaluating it, but it's finding the antiderivative, as with, 99% of these things. I'm just going to go ahead and put this in our A1 notes. Oh, yeah, that one was So, what should we do here?
Use that change of base thing.
Change of base thing on.
The natural log of 4 of x squared.
So that's the natural log of x squared
Well, that's what it meant.
to the fourth. Okay. So what are you thinking then? Look at that mouse spazzing out.
I just don't remember the formula. Was it like a to the x of log of a equals?
Oh, you're thinking of this.
That.
That. But that allows us to convert an exponential into a logarithm or exponential base e.
So I natural log of x squared is the same as 2 natural log of x. So we take 2 to the 4th power, which is 16, bring that outside the integral. So we have natural log of x to the 4th over x. Use a u substitution, so we get u to the 4th. Change the limits of integration, and there we go.
Yeah. Bada bing, bada boom.
Bam.
It's a U substitution is basically what this problem boils down to. Now, I guess there's a couple of ways to look at it. If we have the natural log of x squared to the 4th, we know that's really 2 natural log of x to the 4th. And we really know that's 2 to the 4th natural log of x to the 4th. Does everybody agree with that?
It's because you use the properties of natural log.
Right, property of natural log to move that power out.
Gotcha.
So we could, once we rewrite this, I mean, and we don't even have to rewrite it like this, but I think if we do rewrite it like this, it's a little bit clearer what's happening, right? Because it's this thing over this, finding the antiderivative. Well, if we let u equal natural log, then du is 1 over x, which accounts for that 1 over x dx. That's it. It's the done with that. You know, and again, like if we're thinking of this 4 as on the outside, you know, even from the original integral, we could have said let u equal to the natural log of x squared. Even if you didn't recognize the properties of exponents, then you do your du. Assuming you remember to take the derivative correctly, 1 over x squared times the derivative of x squared dx. And there you have it. There's your 2 over x dx. We don't have a 2 here, so we can put it multiply by 2.5 if we wanted to do that. Or we could just say that 1/2 du is 1 over x dx and substitute here. So either way you look at it, it's a u substitution. So that's why it's really helpful to remember, you know, the antiderivative formulas we have in 8.1 and also like the derivatives. It's super helpful to recognize, oh hey, that's the function and its derivative. It's a u substitution. Super helpful. Okay. Does that make any sense? Do y'all have any questions about that? All right, we'll continue with 8.2. So these first two were just identifying the things we need to identify in order to integrate by parts. So we'll start off with this one, x times e to the x. Again, perfect candidates for integration by parts when you have two products of x, two functions of x multiplied together, which we do. Okay, so we have to identify u and dv. So what should we let u equal? X, if we're going to stick with the protocol, we're going to let x, in this instance, it's not going to matter, because either if we choose x or e to the x, both of those factors are easy to integrate and differentiate. But in a situation where you have a function that involves a logarithm, you know, those are hard to integrate but easy to differentiate. So we're just going to stick with the protocol. The rightmost letter was our algebraic function, x. We're going to let u be that. Therefore, dv is e to the x dx. So you always identify those two first. Then we take the derivative of u and the antiderivative of v. So then our integration by parts tells us that this original integral given to us is equivalent to u times v, uv, minus the integral of v times du. uv minus the integral of v du. We can integrate that. Pretty straightforward now. And we'll have a constant here. Technically, you got a couple of constants, but we'll call it one constant at the end. And there you have it. Any questions? So I'll give you all a couple minutes, 5 minutes to find the antiderivative for x cosine x.
Just like a Zula drive. Water gets under the book because it's smeared too much.
Wow. That's
Pretty experience.
Okay, so there's our setup.
Try this.
Ux dv cosine x dx, and where we're at here.
Oh, this also sparkling.
That's u times v minus the integral of v du. And so we have x sine x. We have minus integral here, minus cosine, minus minus cosine. So x sine x plus cosine x plus c. Anybody have questions on that? Not bad, right? You got derivatives and antiderivatives involved, so you've got to definitely keep those straight. Otherwise, when you write out uv minus the integral of v du, you know you're already wrong in crucial steps. Okay. All right. So similar kind of thing. X ln of x. We're going to let u be the leftmost algebraic in this case, or sorry, logarithmic in this case. Natural log of x is our u. Because if we let dv be natural log of x dx, then you have to integrate that, and we don't want to do that. I mean, we can, but then it's another integration by parts to do that.
Yeah.
Okay, so u is ln. This is a logarithm, and this is an exponential. I mean, algebraic. So our derivative here for u, du is 1 over x dx. And then v is the antiderivative of x, which is x squared over 2. All right. So that is equal to u times v, x squared over 2 times natural log of x, minus the integral of v du. V du. All right. Any questions? You want to simplify that before you find the antiderivative. Move over here. We've got, what do we have? 1/2 x dx. Still carrying this thing around. And we've got x to the second over 2, so minus 1 over 4 x squared. Let's see. Is that what you got? Anybody have any questions there? So you can perhaps end up doing integration by parts more than once. You can do it more than twice, etc. It really just depends on the functions that are present. But the thing is when you do integration by parts, it's sort of like this, you're sort of like slowly whittling away at the product until you usually you don't have a product left. We'll see instances where we do and how to handle those. Algebraic function and our trig function. So we're going to let u be our algebraic, x squared, and our dv then is cosine x dx. du is 2x dx. And v would be what? It's antiderivative of cosine. Which is sine. So when we go through this once, we have that our original integral x squared cosine x dx is u times v minus the integral of v du. So the original integral involved x squared times a trig function. Now we have this linear times a trig function. We've sort of worked it down a power. It is simpler, I guess, with that regard, but it's still a product of two functions. Right, we've got our 2x and a sine x, so that is integration by parts once again. You know, really, if you want to be technical and fancy, you're going to choose different variables. We've already used u and v, so they're already reserved for x squared and sine x. So you should use different variables here if you're going to be technical about this. But it is, you know, again, same process. You know, call this u hat or something. Whatever makes sense to you. I don't know. You're probably in physics. You've probably seen the hat notation. And we're also going to identify dv hat. If you end up using u and dv again, it's not the end of the world. I wouldn't take points off for it, but to be technical. Okay, algebraic function for u, the rest for dv. Okay, derivative here now. Derivative is 2 dx. And the antiderivative of dv gives us v equals 2 minus cosine x. Sorry, v hat. Or I don't know, whatever. Call it a and b if you want. Okay, so the x squared sine x, totally fine, we're leaving that alone. So this is, you gotta be careful when you do this more than once, because this integral here is getting broken up into two separate pieces. It's getting broken up into another uv minus the integral of v du, but you have that minus out in front already, so you've gotta be careful with that minus. It's going to go to both things. So we're just going to put it out right here for a minute, and then write out this for integration by parts. So we have u times v. We have a minus 2x cosine x minus the integral of v du. So minus the integral of negative 2 cosine x dx. So don't get ahead of yourself when you're plugging stuff in. Just plug it in as it's supposed to go in, and then you can start reconciling the signs, right? They can either say, all right, well, the negative in front of the integral and the negative 2, that's going to make that a positive, but then I have this other negative out front that's going to make it a negative again. You know, you can start reconciling all that stuff. But put it in sort of face value first, just so you're not messing up. Okay, and then we'll go from there. Does anyone have any questions about that, what we have? Okay, so we have our x squared sine x. We have, how do we want to do this? We've got a minus 2x cosine x. And then we have a positive integral here with distributing this negative out front. We have a negative integral of 2 cosine x dx. Or, I guess maybe more appropriately, that's just now a constant times a function of x, and we don't have two functions of x being multiplied anymore. So no more integration by parts necessary here. This is what we're dealing with. Anyone have questions? Go ahead and finish this out. So there's our final answer.
So every time you do it, you have to subtract the new integration by parts
Yes.
completely.
Yeah. Yep. Because you mean right from right here?
Mhm.
Yeah. Every time we iterate this again, like if we had another integration by parts with this, that minus is still out in front of the two things that we break this up into, right?
So you take like all of that that's down there and subtract a new integral
Yeah.
by parts.
Yeah. Any other questions about that? So you could imagine, like, if that were like x to the fourth, that would be a pain. You would have to do integration by parts 4 times. I don't know if I put it in. I didn't put it in. There's a thing called tabular integration that really expedites the process of using integration by parts more than once. It's in your textbook as like an exercise. If I can put it in our notes, I will. It's really abstract in how they presented it. So we'll just go ahead and talk about it. And then if I can maybe find it in your textbook really quickly, I'll put it in the notes. But so it's really just an expedited process of integrating by parts. And what do we have? We had x squared cosine. So, x squared cosine x. So the process is kind of the same. You've identified the U and the DV. So we're going to put the U's over here, the U right here, and the DV over here. And I don't know. We're just going to make a mental note that these are that's our U, that's our DV. The thing we identify as U, we take the derivative of it, right? So we take the derivative of x squared. We take the derivative of 2x, we take the derivative of 2, and get 0. No more derivatives to take. With the dv thing, we've identified that cosine x, so we still do the antiderivative here. So the antiderivative again. And then the antiderivative again. So more or less, that really hasn't changed. Is everybody okay with that? The trick is, we saw with the integration by parts, you had that negative, and then you broke that up into two more things, so that second integral actually became positive. The third one would become negative if you had a third one. So with our u's over here, the first one starts out, we have a positive, but then we have a negative, and then a positive, and then a negative. So we need to just alternate signs on the u column. Okay. Then what we do is we sort of cross multiply. We have a positive x squared times sine x. We've exhausted that one, so we go back to this one. We've got our negative 2x times negative cosine x. And then we have our positive 2 times negative sine. And there you have it. There's the same antiderivative we came up with. So it's, I don't know, akin to like synthetic division, where you just ignore the coefficients. It's akin to a matrix, where you just look at the coefficients. It's kind of analogous to those processes. If at any point you choose to go, instead of going diagonally to just get a product, if at any point you choose to go vertically, then you've got to stick an integral in front of it. So like for instance, I could also have taken this stuff here. I could have also taken my table and said that the integral of x squared cosine x, maybe I start off by saying x squared times sine x. But say for whatever reason, sometimes you have to do this too. Say for whatever reason I wanted to go vertically like this. I'm still going to have that minus 2x sine x, but I have to take the integral of it because I've gone vertically. So at any point you choose to go vertical to multiply those functions, you've got to put an integral in front of it. So minus 2x sine x, where do we see that here? We saw that here. So we'll look at a couple more like this too. I don't care if you use tabular integration versus integration by parts, it's the same thing. So it's just a little more efficient that way, especially if you have to do it multiple times. All right, any questions about that? So x squared e to the negative x. Let's let's look at it with the tabular integration, and then we'll probably pass exams back. And when we come back on Thursday, we'll look at this with, the regular integration by parts, UV minus the integral. So we'll start off with the tabular integration. We still identify u and dv the same, so our u is going to be x squared, our dv is e to the negative x. On the u side, we take derivatives, so again, 2x, 2, and 0. I guess we don't have to write out the 0, but we will. Okay, so derivatives along that column, antiderivatives along e to the negative x. So what's the antiderivative of e to the negative x?
Negative e to the negative x?
Yeah, good. Negative e to the negative x. Antiderivative of negative e to the negative x? E to the negative x, and so on and so forth it goes. We're going to stop there with 0. And as you could expect, like some of the functions we identify as u don't eventually end up with a 0 derivative. So you've got to kind of know what's happening as to, like, if this function didn't 0 out as a derivative, you got to know when to stop. So you can, if you kept going, then you would have infinitely many terms because it never zeroes out. So I guess that is a disadvantage to using this. You kind of get to the point to where you're like, I got all these terms hanging out, what do I do with all of them? Okay. Alternate the sign, start with positive, negative, negative. Cross multiply. We've got a positive x squared times a negative e to the negative x. We have a negative x squared e to the negative x as our first term. Cross multiply again, negative 2x times e to the negative x gives us a negative 2x e to the negative x. And then once more, because we lined up our 0th derivative, our 0, how did I say that? The derivative that ended up as 0, I guess, with this function here. So we've got one more of these cross multiplications to do. Minus 2e to the minus x. Okay, there's nothing to cross multiply with 0, so that's how we know we're done with that. Does that make sense? We'll look at it the long way next class period, but that's our antiderivative. So just if you're interested in section 8.2, if you look at exercise number 71 in the textbook, you can access it online. Exercise 71 gives you sort of a general approach to tabular integration, but this is how it works in practice. Okay. Does anyone have any questions about that?